Hello everyone, this is Professor Roman. Let us continue the field theory lectures. In the last lecture we started our look at Galois theory by covering some preliminaries on symmetric polynomials and Newton's theorem. In this chapter I want to give an overview of this subject. Galois theory sits atop of a body of work that really began about 4,000 years ago concerning the question of how to solve polynomial equations algebraically. In other words, how to solve an equation like this where the coefficients belong to a base field by applying a finite sequence of the four basic arithmetic operations: addition, subtraction, multiplication, and division, along with the taking of nth roots for various values of n bigger than or equal to 1. And I'm including 1 just for convenience. So let's refer to the four basic arithmetic operations and the taking of various roots as the 5 basic algebraic operations. Of course, 4,000 years ago, they wouldn't have expressed the problem in this language, and it was restricted to quadratic equations, but we've come a long way in 4,000 years. Note that if F is a field and alpha and beta belong to F, then any application of one of the 5 basic algebraic operations to these two elements will produce an element that's algebraic over F. A lot of the times it'll produce another element of F. The 4 basic arithmetic operations applied to alpha and beta leave you still in the field F. The taking of an nth root of alpha may or may not belong to F. Now, it's often said, I guess, that the crowning achievement of Galois theory is that it can be used to prove that there's no general algebraic formula, similar to the quadratic, the cubic, and the quartic formulas, that will give the solutions to every polynomial equation of a given degree, d, greater than or equal to 5. Well, to understand why this is the case, we need to ask ourselves exactly what we mean by a general algebraic formula. So that's what I'm going to try to do now. An examination of the quadratic formula for the general quadratic polynomial shows that this is a well-formed algebraic expression involving rational numbers, the independent variables a, b, and c. Since this is the general quadratic, a, b, and c are thought of as independent variables, and of course the 5 basic algebraic operations. And using this as a model, we have the following definition. Let F be a field and let V be a set T1 through Tn of independent variables over F. Then an algebraic expression alpha is an algebraic formula over F with these variables if, so this is the definition of algebraic formula, if there is a sequence alpha 1 through alpha m of algebraic expressions. And when I say algebraic expression, of course, I mean a legal expression, a well-formed algebraic expression, with the following properties. Alpha 1, the first element of the sequence, is either in an element of the base field or a variable. For each k bigger than or equal to 2, alpha k is formed by applying one of the 5 basic algebraic operations to elements from this set: the base field elements, the variables, or the elements of the sequence that have already been defined. And finally, the last element of the sequence alpha m is alpha. I'm going to call a sequence such as this a construction sequence for alpha over f. And I guess I should add with variables v and say that alpha has an algebraic formula over f, or is constructible by algebraic formula over f, or expressible by algebraic formula over f. That variety of language here, it all amounts to the same thing. You might have noticed that the quadratic formula has this symbol plus and minus, so it's actually two formulas. And so when we speak of an algebraic formula for the roots of a polynomial, we really mean one formula for each root. Now, the algebraic formulas we're looking for are general algebraic formulas for the roots of all the polynomials of a given degree. Quadratic formula, cubic formula, quartic formula are such. But to make a formal definition of a general algebraic formula, first we need this. Let f be a field and let t naught through tn be a set of independent variables over f. This polynomial, the t's are the coefficients. This is a polynomial over the field of rational functions in the t naught, in the t's, is called a general polynomial of degree n over f. Okay, a couple of things. When you look at this, your first thought is that this is a polynomial over f, but it's not, because the coefficients are these independent variables over f. So to get a field that includes the coefficients, we have to jump to the field of rational functions in these variables over f. If we just use the polynomials in the variables over f, we would have polynomials over a ring and not over a field, and we don't want that. Okay. The other thing is that there are other definitions of a general polynomial. Some authors will alternate the signs. Another version of the general polynomial is this, because this is the polynomial whose coefficients are, except for sign, the elementary symmetric polynomials. In fact, this is the definition I gave earlier for general polynomials. So it looks like I'm giving two different definitions, but in fact, the elementary symmetric polynomials in these variables are also independent variables, and we proved that in Theorem 3.7 in the last lecture. So these minor differences in what might be considered three definitions really don't amount to much. Okay? They're equivalent. I should also mention that sometimes the term generic polynomial is used in place of the term general polynomial. I kind of favor that myself, but the term generic polynomial has a different, related but different and more complex meaning in field theory. So we're going to stay away from the word generic. I'm going to try anyway. Definition then. Let f be a field and let n be bigger than or equal to 2. A general algebraic formula, or just a general formula, for polynomials of degree n is an algebraic formula over f with variables t0 through tn that gives the roots of the general polynomial of degree n. So, I defined for you earlier the concept of an algebraic formula involving the construction sequence, and then I defined the general polynomial. So now I can define the general algebraic formula as an algebraic formula for the roots of the general polynomial. So the quadratic formula is a general formula, general algebraic formula, for the general quadratic. A, B, and C are independent variables. You are used to plugging in values for A, B, and C any way that is appropriate at the time, so they have to be independent variables. They can't have any algebraic relationships. Now, it is worth emphasizing that just because a general algebraic formula of degree n does not exist, does not preclude the existence of specific algebraic formulas with no variables for the roots of a given polynomial of degree n. So let's take the case n equals 5. We will show eventually that there is no general algebraic formula for polynomial equations of degree 5, but a given polynomial equation of degree 5 may have a specific algebraic formula for its roots. Okay. In fact, there could conceivably be a different algebraic formula for each polynomial of degree n. Okay, so the absence of a general algebraic formula is just that, and we should not read anything else into it concerning specific algebraic equations. On the other hand, if there fails to be a formula, an algebraic formula for the roots of even a single polynomial of degree n, just one is all it takes, then there can't be a general algebraic formula, because the general algebraic formula is valid for all of a given degree, valid for all polynomials of that degree. Okay? Let me say it again. If there fails to be an algebraic formula for the roots of even a single polynomial of degree n, just one, then there can't be a general algebraic formula for all polynomials of degree n. And that's critical, because that's how we're going to show that there is no general algebraic formula for degree 5 or greater, by finding a polynomial whose roots have no formula, no algebraic formula. Okay, so down to business, so to speak. The road to showing that a general formula does not exist for polynomials of degree n equals greater than or equal to 5 is to first consider what it means to say that a single element alpha can or cannot be expressed by using only the 5 basic algebraic operations. So here is the definition. This term that I'm using here, expressible by formula, constructible by formula, is my term. I don't know whether other authors use these terms or not. I would guess it's not. I would guess not. So you can be the judge yourself of whether they are helpful terms, but I think they are. Let F be a field. An element alpha in F bar is expressible by formula or constructible by formula over F. Now, perhaps you can guess what's coming. It's got to have an algebraic formula, as we first discussed, a construction sequence. But there can't be any variables, because those don't go away, and we're not going to get a specific element in F bar if the formula has variables in it. So that's exactly what this definition says. Alpha is expressible by formula if it has an algebraic formula over F, in other words, a construction sequence, with no variables. And here it is specifically. Alpha is expressible by formula over F if there's a construction sequence with the following properties. Alpha 1 is in the base field, and for k bigger than or equal to 2, the element alpha k is formed by applying one of the 5 basic algebraic operations to the elements from the base field and or the elements that are already in the construction sequence. And finally, alpha m is alpha. So it's just a construction sequence with no variables. Now, it should be clear that if beta is an algebraic formula over F with variables, then by replacing each variable with an element from the base field, we will get an element that is expressible by formula. Excuse me. After all, it doesn't matter whether we do the replacement of variables by constants from the base field before or after we make the construction sequence. So let's look at an example. Suppose T1, T2, and T3 are independent variables over F, then this is an algebraic formula. I just made it up. It's of no real value. Here's a construction sequence. T1, T2, T3, T1, T2. So at each stage, I'm applying one of the 5 basic algebraic operations to the previous elements and tossing in any elements of the base field if I should need them. I probably didn't do a good example here. I should maybe change this to twice this, so I can throw something in from the base field, but I think you get the idea. So I am slowly constructing this mess here, one basic algebraic operation at a time. And you can see that the order is not necessarily fixed. I could have reordered some of this and gotten technically a different construction sequence with the same end result. Okay. So construction sequences are not at all unique in general. Now, if A, B, and C are elements of the base field, then I could substitute them for the 3 variables and get something that looks like this. And here's the construction sequence. So this is kind of much ado about nothing, but it makes the point that you can do a general construction sequence with variables and then substitute constant values for the variables, or you can just do the construction sequence with the constants in the first place. You'll come out in the same place. Now, extensions, field extensions, in which every element is expressible by formula are going to be important to us. An extension FE is expressible by formula or constructible by formula if every element of E is expressible by some formula over F. It doesn't have to be the same formula, obviously it can't be. And we'll also say that E is expressible or constructible by formula over F. Okay? And I'm going to denote the class of all field extensions that are expressible by formula over F. Actually, extensions expressible by formula, so I don't need over F, by script E. This is an element-based definition, like the definition of separable extension or algebraic extension. An extension is algebraic if every element is algebraic over the base field. An extension is separable if every element has minimal polynomial with only simple roots. Okay. Unlike the other extensions like finite extensions and normal extensions that are global, not element-based. Any extension that's expressible by formula is algebraic because each element is constructed with a construction sequence and is algebraic over the base field. Also, if we have elements S1 through Sn in E that are expressible by formula over F, then any rational function of S1 through Sn is expressible by formula, right? Because we are simply, to get to the rational function, we apply the 5 basic algebraic operations. Theorem: a finitely generated algebraic expression is expressible by formula if and only if each of the generators is expressible by formula. This is the same kind of result we looked for separable extensions. If the generators are separable, the whole extension is separable. For algebraic extensions, if the generators are algebraic, the extension is, and it works here too. The class E of all field extensions that are expressible by formula, and I did it again, I would be saying E is expressible by formula over F, or Fe is expressible by formula. So this is redundant. This class is strongly distinguished, so we know it has very nice properties. To see that E has the tower property, suppose we have our little 2 tower here. If the full extension EL is expressible by formula, then the lower step is 2, because it's element-based. If all the elements of L are constructible over E, then so are all the elements of K. But also KL belongs to the class E, because if we take an element of L, it has a construction sequence over E that can be thought of as a construction sequence over K, where we don't use any elements of K other than the ones that are in E. Also, if the individual steps belong to E, then to see that the full extension belongs to E, note that because the process of expressing an element by formula is finitary, it uses only a finite number of steps and a finite number of elements, for any beta in the top field, there's a finite set from K for which beta is expressible by formula over E with that finite extension, with those adjoined, the finite elements adjoined. So we haven't dropped all the way down to E, but we've got closer. But we can concatenate the sequences that construct each element K1 through Km over the smallest field E into a single construction sequence. You may have to think about that. And that construction sequence constructs every element K1 through Km. Now we have those elements available. We can extend or append the sequence that constructs beta from both E and K1 through Km, because they are now available to us. This construction sequence idea is very flexible, really. So the full extension is expressible by formula. As to closure under arbitrary composites, suppose we have a collection of fields containing F, and that each individual extension, FEI, is expressible by formula. Every element in the join or composite of the family is a polynomial, because we're dealing with an algebraic extension here, is a polynomial in S1 through Sn, where the SIs are in the union of the family, so they're somewhere in the family. But each SI is expressible by formula over F, and therefore so is alpha. And so this extension, the join here or the composite here, belongs to E. As to the lifting property, suppose that Fe is expressible by formula and that Fk is any field extension. The elements of Ek are rational functions in the union, E union K, elements from either E or K. And since we can construct any element of K over itself and any element of E over K, we can construct any rational function. In other words, any element of Ek over K. And so that's the lifting property.